Have you ever wondered why we use degrees but then suddenly switch to radians in higher math? To understand how these systems work, we take a ray OP with one end pinned down at a fixed point O, while the other end is completely free to rotate. When this ray rotates about that fixed point O, it starts moving from its initial position and reaches its terminal position. The amount of rotation between these two positions tells us the measure of the angle formed. In other words, the larger the rotation, the larger the angle. To measure this amount of rotation, let's begin with the first system, the degree measure. In this system, a complete revolution is taken as 360 degrees. If we divide this full rotation into 360 equal parts, each part is called 1 degree. So, if our ray rotates through one of those parts, it forms an angle of 1 degree. To measure rotations smaller than 1 degree, each degree is further divided into 60 minutes. And for even smaller rotations or highly precision amounts, each minute is split into 60 seconds. Don't get confused by the name. These minutes and seconds have nothing to do with time. They are simply units of angular measurement for very precision rotations. Now let's move to the second system, the radian measure. Unlike the degree system, this system defines its unit angle using the radius and the arc of a circle. So first, let's understand what 1 radian actually means. To do that, let's look at our ray OP. As the ray rotates, its tip point P traces a perfect circle. Since point O remains fixed, the distance OP is the radius of this circle. When point P starts moving from its initial position along this circle's boundary and covers an arc length that is exactly equal to the radius of this circle, then the angle formed by the ray at the center O is defined as 1 radian. To understand this clearly, imagine taking that curved arc and straightening it out into a line. If you lay that line right on top of the radius, you will see they are exactly the same length. The endpoints match up perfectly. Now notice the pattern that begins to emerge. If point P covers an arc length equal to 1 radius, it forms an angle of 1 radian. If it covers an arc length equal to 2 times the radius, it forms an angle of 2 radians. And for a length of 3 times the radius, it forms 3 radians. This means that the total angle in radians is just the number of radius-sized pieces that fit into our arc length. So to find the angle theta, we simply take the total arc length, let's call it L, and divide it by the radius r. From this pattern, we get the fundamental formula for measuring angles in radians. Theta equals L divided by r. By applying this formula to a complete revolution, in which point P travels a distance equal to the circle's circumference, which is 2 pi r. If we divide this distance 2 pi r by the radius r, the r cancels out. This means a complete revolution forms an angle of exactly 2 pi radians at the center. Now, if the ray completes only a half revolution, point P covers half the circumference, forming exactly half of that angle, which is pi radians. And since we already know from our degree system that a full revolution is 360 degrees, a half revolution equals half of that, which is 180 degrees. This gives us one of the most important relationships between the two measurement systems. Pi radians equals 180 degrees. Keep in mind, whenever you need to convert degrees to radians or radians back to degrees, this is the only relationship you need to use. For example, to convert 2 pi by 3 radians into degrees, simply substitute pi with 180. That gives us 2 times 180 divided by 3, which simplifies to 120 degrees. Now let's go the other way. To convert 315 degrees into radians, just multiplied by pi and divide by 180. That simplifies to 7 pi by 4 radians. Now you know how angles are measured in both degrees and radians and how the two systems are connected. So why do mathematicians prefer radians? Because radians directly relate an angle to the radius and the arc length of a circle through the simple formula theta equals L divided by R. This makes many mathematical formulas simpler and more natural, especially in trigonometry, calculus and physics. That's why higher mathematics almost always uses radians instead of degrees. That's all for today. Thanks for watching.